Welcome to the Fast Neutron. This is a channel I've set up to talk about all things nuclear. I'm starting a video series here aimed at explaining some of the basic concepts behind nuclear science and engineering. Now my goal here is to create something fun and engaging, so I'm not going to be going into the level of detail you'd find in, say, a nuclear engineering grad program with these videos. Rather, I want to help you build intuition on the subatomic world and how we leverage it to power our lives in nuclear reactors. So I hope you learned something new and enjoy this series. For this first video, I'm going to be covering some of the absolute basics. We're going to start off with a quick discussion on atoms as a jumping off point. We'll talk about the subatomic particles that they're made of, their overall structure, and some of the conventions for how we describe them. Next, we'll talk about the strong nuclear force, which underpins so many of the phenomena that we take advantage of in the field of nuclear engineering. And then finally, we'll bring things home with a discussion of nuclear binding energy, and I'm going to walk through the semi-empirical mass formula with you. Alright, enough logistics, let's dive in. Atoms themselves aren't elementary particles. They're actually made up of a number of subatomic particles, and the first one we'll highlight here is the proton. It has a mass of about 1.6 times 10 to the minus 27 kilograms, which in plain speak is not very much, and it has an electric charge of positive 1. Next up is the proton's negatively charged friend, the electron. It has a mass of about 9.1 times 10 to the minus 31 kilograms, orders of magnitude smaller than even that of the proton, and it has an electric charge of negative 1. Finally, there's the neutron, which, although unbiased, is definitely the coolest of the three. It has a mass slightly larger than that of the proton, and it is electrically neutral with a charge of 0. Now, in case you're in the part of the population that struggles to make sense of numbers as small as 10 to the minus 31, which I think is everyone, there is a way to put these masses into a slightly friendlier form, which you may see in a lot of texts, and it comes to us courtesy of Albert Einstein's most well-known equation, E equals mc squared. This equation says that mass and energy are really just two sides of the same coin. Because of this, we can actually express the masses of these particles in terms of their rest mass energy. That's the amount of energy you would get from converting 100% of an object's mass into energy. So let's do a quick calculation to figure out the rest mass energy of a proton. So we take our expression E equals mc squared, and we plug in the proton's mass. Now we get a value of 1.503 times 10 to the minus 10 joules. While this is the rest mass energy of the proton, this number, like the proton's mass expressed in kilograms, is still pretty unsightly. To fix this, let's put this energy in terms of electron volts. From the relation below, we can see that 1 joule is equal to 6.242 times 10 to the 18 electron volts. Now while electron volt is a pretty weird name for an amount of energy, the textbook definition is actually pretty intuitive. An electron volt is the amount of kinetic energy an electron would have if you allowed it to accelerate across a 1 volt potential. I'm going to throw a quick visualization of that up here on the screen. So we're going to track this electron's energy as it goes across this potential. The 1 volt potential here causes the electron to feel a force to the right. At the instant it reaches the end of this 1 volt potential, the amount of kinetic energy it has is exactly 1 electron volt. In the world of subatomic particles, this tiny unit of energy is much more convenient to work with compared to joules. So with this understanding, let's put the rest mass energy of the proton in terms of electron volts. Then, let's do a quick conversion to mega electron volts. Mega here is just the prefix for 1 million. Now we've arrived at a number which is a lot easier to think about. 938 million electron volts, or 938 MeV. Now, from E equals mc squared, we know if we take this energy and divide by c squared, we get the mass of the proton. And because c squared is just a constant, lots of times you'll see that we just leave it out. So the mass of the proton can be written as 938 MeV. That's a lot of energy packed into such a tiny particle. If we go through the same process for the neutron and electron, we get the following results. You can see that the neutron has a rest mass which is just a little bit larger than the protons, at 939 MeV, and the electron has a rest mass of just over half of an MeV. Alright, now that we're familiar with the subcomponents of atoms, let's actually go and build one. So right here we've got 2 protons, 1 neutron, and 2 electrons. Protons and neutrons are packed tightly together within the nucleus, which lies at the center of any atom. Electrons aren't part of the nucleus. Instead, they exist in orbitals at the periphery of the atom. Now I can already hear a few of you yelling at your screen that this isn't actually what an atom looks like, and of course you'd be right. One, this absolutely isn't to scale, and also atoms don't look like the solar system. Electrons don't travel around the nucleus in nice orderly paths like this. In reality, electron orbitals are much more fuzzy. The modern quantum understanding of electron orbitals models them more like a cloud, and then within these clouds, it's not possible to say exactly where an electron is. You can only predict the probability that they're within one region or another. Now, this is as good a time as any to talk about the notation that we use to describe atoms. The notation looks a little something like this. 3 symbols arranged like so, which can communicate exactly what atom we're talking about. Within this notation, we replace X with the chemical symbol that corresponds to our atom's element. So for the example here, this is an atom of helium, so we use He. We replace Z with the number of protons in the atom. Now, of course, if you know what element an atom is, you also know the number of protons it has. So for helium, it's 2. And lots of times, for this reason, the C is just left out. We replace A with the total number of nucleons, that is, protons and neutrons that the atom has. So here, it's 3. And there you have it. This is an atom of helium-3. This notation is capable of describing any isotope. Isotopes are distinct varieties of a single element. Isotopes of the same element are distinguished by their mass number. That's the number of protons and neutrons added together. So they have the same number of protons, but different numbers of neutrons. An element's isotopes all have basically the same chemical properties, but they have different masses and their nuclear properties can vary wildly. Here are a couple more examples. This is an atom of helium-4, by far the most common isotope of helium in the universe. And here's an atom of lithium-7, with 3 protons and 4 neutrons. Okay, with all this out of the way, we now have an understanding of the building blocks which make up atoms. In the next section, we'll discuss some of the forces which affect protons and neutrons within the nucleus. Here's the thought experiment for you. If you have 2 protons floating in space, and you grab one of the protons and move it closer to the other one, what's going to happen? If you guess that the other proton will be repelled, you're right. But why is this the case? Well, it has to do with the electric fields associated with each of the protons. All charged particles create an electric field which permeates all of space. As you can see from the example on the screen, the strength of the electric field falls off as you get further away from the proton. For a single proton floating in space, there's no other field to act on it, so the proton stays put. Once we introduce a second proton, they interact with each other's fields and they feel a repulsive force. This is why like charges repel one another. The mathematical relationship which describes the forces that charged particles impart upon one another is Coulomb's law. Here, F is the force that a charged particle will feel, Q1 and Q2 are the charges of each particle, R is the distance between the particles, and K sub E is a constant. Let's plot the force that these protons feel as the distance between them changes. So we start with the relative distance of 1. As we bring the protons closer together, you can see that the forces they exert upon one another increase very quickly. In fact, they increase asymptotically as R approaches 0. This is due to that 1 over R squared term. It blows up when the distance between the protons gets very small. What this simple example shows us is that if we were to pack a collection of protons very close together in a bundle, a very strong force aimed at disassembling that bundle would appear. So this begs the question, how can a nucleus even exist in the first place? Surely forcing a bunch of protons next to one another would just result in them flying apart, right? Now this obviously isn't what actually happens though, and we have the strong nuclear force to thank for that. The strong force is one of the 4 fundamental forces, with the others being gravity, electromagnetism, and the weak force. The strong force acts on nucleons to draw them closer to one another. I'm going to plot the potential energy of 2 nucleons due to the strong force as a function of the distance between the nucleons below. Now, the first thing I want to note is that the strong force lives up to its name. It's way more powerful than any of the other fundamental forces. However, an important caveat here is that the strong force is only appreciable at very short distances. For 2 nucleons, the magnitude of the strong force is only large when the nucleons are within a couple femtometers of each other, with a femtometer being 10 to the minus 15 meters. Nucleons themselves only have a radius of around 1 femtometer, so this is a really small distance we're talking about here. The second thing that we notice is that the strong force has both an attractive and repulsive component. When the potential energy is negative, that means that the strong force is attracting the particles towards one another. When it's positive, that means that it's repelling them away from one another. So it repels the nucleons at very short distances and attracts them when they move further away. Because of this, the nucleons assume a stable configuration, almost like they're bound together by a spring. Once we move beyond a few femtometers of separation, electromagnetism takes over, and even though it's weaker than the strong force at short length scales, it falls off much more slowly with distance and becomes dominant further out. Another important thing to note is that the strong force doesn't care about charge. Well, electric charge, that is. From the strong forces perspective, protons pull on protons, neutrons pull on neutrons, and they both pull on each other. The strong interaction actually acts on what's called color charge, a property held by the quarks that make up all hadrons, of which protons and neutrons are just two examples. And the strong force is mediated by particles called gluons, which bind quarks together. Something I find really interesting is that the strong force, which holds protons and neutrons together, is really just the residual component of the strong interaction, which acts on quarks. Within protons and neutrons, the color charge of quarks sums to 0. Protons and neutrons are color neutral. With this in mind, it seems pretty weird that the strong force acts on nucleons in the first place, as they're effectively neutral particles from its perspective. But an analogy which helps to explain this can be found in London dispersion forces. London dispersion forces are intermolecular forces, and they emerge from momentary imbalances in charge that allow otherwise electrically neutral atoms and molecules that are in close proximity to attract one another. These forces are much weaker than the electric forces which actually hold the molecules together, though. The strong force can sort of be thought of as the nuclear version of this. Even though protons and neutrons are color neutral, particles called pions can briefly leak out of nucleons and act as a force carrier which attracts them to one another. Now, let's talk about the role that neutrons play in keeping nuclei together. 2 protons is not a stable configuration for a nucleus. However, if we add a neutron, we get a stable nucleus. This is just the helium-3 nucleus from earlier. Now, there's a couple of reasons why adding neutrons increase the nucleus's stability. First, adding neutrons increases the number of nucleons that are available for strong interactions without increasing electrostatic repulsion, since neutrons are neutral. Neutrons also help to space out protons from one another. Finally, having both protons and neutrons helps nuclei cooperate with the Pauli exclusion principle, which states that no 2 identical fermions can simultaneously occupy the same quantum state in a system. While neutrons and protons are both fermions, they're distinguishable, so they're not held to this standard, at least with respect to one another. The end result of this is that having a combination of protons and neutrons allows for the lower energy quantum states within a nucleus to be more efficiently filled. This lowers the nucleus's overall energy and increases its stability. So, neutrons basically act like glue. They help hold nuclei together. Now that we know about the strong nuclear force and how it allows for the formation of nuclei, let's talk about nuclear bonding energy and wrap things up with a semi-empirical mass formula. Okay, so here we have a helium-4 nucleus, 2 protons and 2 neutrons. And I'm going to pose what seems like a pretty simple question. What would you expect the mass of this helium-4 nucleus to be? Seems straightforward enough. Here we have values for the masses of a proton and a neutron. This AMU unit, by the way, is the atomic mass unit. It's defined as being equal to exactly 1/12 the mass of an atom of carbon-12, 1.66054 times 10 to the minus 27 kilograms. And just a quick note, we often symbolize the atomic mass unit with just the letter U. Now it stands to reason that the mass of the nucleus will just be the sum of its components, so we could write out an equation for that. The nucleus's mass should be the number of protons it has times the mass of a proton, plus the number of neutrons it has times the mass of a neutron. So we sub in 2 and 2, then we plug in the proton and neutron masses, and we arrive at a total mass of 4.031883 atomic mass units. So that's our prediction. But if you actually go and measure the mass of a helium-4 nucleus, you'll get a different value, one slightly smaller than the one we calculated here. The true mass of a helium-4 nucleus is 4.001506 atomic mass units. So we are off by 0.03 atomic mass units. The mass of our nucleus is less than the sum of its parts. So what's going on here? This is what we call the mass defect. This missing mass is a result of the fact that because the nucleus is in a stable configuration, it would take energy input from us to pull it apart into its constituent parts. The energy required to separate all of the nucleons in a nucleus from each other is its binding energy. Through conservation of energy, it's equally valid to say that it's the amount of energy which would be released when a nucleus is formed from a collection of separate nucleons. Once again, Einstein makes an appearance to explain things away. This missing mass is just the difference in energy between the 4 nucleons when they're out on their own, and the 4 nucleons when they're bound together in the nucleus, which is a more stable and lower energy configuration for them. If we plug in our mass defect, we see that the binding energy of the helium-4 nucleus is just over 28 MeV. So because the nucleons are pulling on each other through the strong force, it would take a little more than 28 MeV of energy from us to separate them. So, that original mass formula we came up with, well, it is actually wrong, but we can add a correction to our formula by subtracting this mass defect. And as we just showed, this is equal to the nucleus's binding energy divided by c squared. This corrected equation we arrived at is called the semi-empirical mass formula. The first two terms here are really easy to calculate, but figuring out the binding energy is a little more complicated. So let's expand that term out. Okay, so this looks a little wild at first, but what we have here is a function for calculating the binding energy of a nucleus as a function of the nucleus's mass number and its atomic number. The terms A sub V, A sub S, A sub C, A sub A, and A sub P are experimentally determined coefficients, hence the empirical in the name. They're all in units of MeV. Now this equation is only semi-empirical because the form of each of these terms has a theoretical backing in what's called the liquid drop model of the nucleus, which is a crude approximation that treats nuclei as spherical volumes made up of an incompressible fluid. If we take these theoretical terms and attach coefficients to them, and then adjust the coefficients to fit observed data, we arrive at the semi-empirical mass formula. Now, let's talk through the rationale behind each of these terms. The first term is called the volume term, with the form A sub V times A. This describes the strong force between neighboring nucleons. Now, because the strong force has such a short range, if you were to add an additional nucleon to the center of a nucleus, it would only really feel a pull from its immediate neighbors. So adding a nucleon should increase the overall binding energy of the nucleus by a fixed amount, leading this term to scale linearly with the volume of the nucleus, which is just proportional to the number of nucleons in the liquid drop model. The magnitude of A sub V is 15.835 MeV. You'll notice that with the exception of the last term in the equation, which we'll get to, the volume term is the only positive term in this formula. All the others subtract away binding energy to correct the assumption we made in scaling binding energy linearly with the mass number of the volume term. The second term is called the surface term, with the form A sub S times A to the 2/3. This term corrects for the fact that nucleons on the surface of the nucleus will have fewer neighbors than nucleons in the center. So we need to subtract away the missing binding energy of these surface nucleons. Now this term should scale with the surface area of the nucleus. If the surface area gets bigger, that means there's more nucleons on the surface with missing neighbors, so this term should grow in magnitude. The surface area of a sphere is proportional to the volume raised to the 2/3, leading to the surface term's form. As the mass number increases, this term does not scale up as fast as the volume term, which makes sense, because the sphere's surface area grows slower than its volume. The magnitude of A sub S is 18.33 MeV. Next up is the Coulomb term, with the form A sub C times Z minus 1 all over A to the 1/3 power. This term corrects for the fact that we need to reduce the binding energy due to the Coulombic repulsion between the protons. Now, unlike the strong force, electromagnetism has no problems acting at a distance, so all the protons in a nucleus will feel a repulsive force from all the other protons, regardless of if they're neighbors or not. For a collection of Z protons, there will be Z times Z minus 1 ways to pick an ordered pair of them, so this term scales with the number of proton-proton interactions, so to speak. If we model the nucleus as a sphere of uniform charge, we find that its potential energy is inversely proportional to its radius, so we divide by A to the 1/3, since we take the volume to be proportional to A. As we saw earlier in the video, electrostatic repulsion decreases with distance, so it makes sense that this term would decrease if we packed more nucleons into the nucleus and spaced out the protons. The magnitude of A sub C is 0.714 MeV. Now the last two terms are a little more tricky to understand, and we'll start with the asymmetry term. Remember that the Pauli exclusion principle prevents like fermions from taking on the same quantum state in a system. If we had a hypothetical nucleus made up of just protons or just neutrons, the nucleons would be forced into higher energy quantum states than if we had a nice mix of protons and neutrons. This is actually the main reason for the 2-proton nucleus from earlier not being stable. Note that A minus 2Z is equal to the number of neutrons minus the number of protons, so the numerator is just the square of the imbalance between the two. The effect of asymmetry is more pronounced in smaller nuclei than in larger nuclei, so we divide by the mass number. The magnitude of A sub A is 23.2 MeV. Finally, we have the pairing term, with the form delta of A and Z times A sub P times A to the negative 1/2. This describes the effect of spin coupling. Due to the Pauli exclusion principle, it's preferable to have an even number of like nucleons, as there can be one spin-up particle for every spin-down particle. If there's an odd number of a type of nucleon, one of the nucleons won't have a partner to pair off with, and it will lose out on the lower energy state it could have achieved through spin coupling. This delta function captures this. If there's an even number of protons and an even number of neutrons, all protons and neutrons will be spin coupled. In this state, we get an increase in the overall bonding energy of the nucleus, so the delta function takes on a value of positive 1. If we have an odd number of protons and an odd number of neutrons, we'll have two nucleons that aren't spin coupled, so we get a decrease in the overall bonding energy, and the delta has a value of negative 1. In any other case, we'll have one uncoupled proton or neutron, so this basically cancels out the effect of the spin coupling of the other species. The a to the negative 1/2 term is more or less empirically determined, as a theoretical calculation with the liquid drop model would give us a 1/a term instead. But a to the negative 1/2 is found to fit real-world data better. The magnitude of a sub p is 11.2 MeV. Now that we have an understanding of the phenomena behind binding energy, I want to do a couple calculations to show this formula's real-world applicability. Let's use the binding energy formula to answer the following question. For a collection of 56 nucleons, what number of protons will maximize the binding energy? Let's plot the atomic number on the x-axis and the overall binding energy of the nucleus on the y-axis. We see that the binding energy takes on a sort of parabola shape as a function of the atomic number. There's a specific combination of protons and neutrons that gives us the maximum possible binding energy. Let's talk about all the terms of the binding energy equation and how they're changing here. The volume and surface terms are constants across this curve, since they only depend on the mass number, which we fixed at 56. When we have too many protons, the Coulomb term also increases considerably to the detriment of binding energy. When we move away from an even split of protons and neutrons in either direction, the asymmetry term gets really large, and so the overall binding energy of the nucleus falls. Although it's really hard to see, there is a small zigzag pattern within this plot, which is attributable to the pairing term. The binding energy is slightly higher when there's an even number of protons and neutrons. It's just hard to see since this is a fairly heavy nucleus. The maximum point on this curve occurs when there are 26 protons, which corresponds to iron. Iron 56 is one of the most stable nuclei out there, so it makes sense that it's at the top of the curve. Let's do another quick example, this time for a collection of 238 nucleons. How many protons will maximize binding energy? If we plot the curve and take a look at the maximum, we get an answer of 92 protons, which corresponds to uranium. Uranium-238 is the most common isotope of the element on Earth, making up around 99.3% of all the uranium that we dig out of the ground. One quick point of note here is that although the overall binding energy of uranium-238 is much higher than that of iron-56, the binding energy per nucleon is lower. I'm going to close this out with one last plot to show the results for every isotope out there. This is going to need 3 axes. On the x-axis, we'll have all mass numbers from 1 to 250. The y-axis will correspond to the atomic number. Each point on this xy plane is a unique combination of protons and neutrons. On the z-axis, we'll plot binding energy per nucleon for these nuclei, so we're seeing how tightly bound together the nucleus is on a per nucleon basis. We get a plot that looks like this. So all the concepts we talked about previously have built up to this plot. Mass energy equivalence helps us explain the mass defect in the context of nucleons bound together by the strong force. And the terms in the binding energy equation from earlier cause this surface to take on the shape that it has. Each slice of this plot shows how, for a set number of nucleons, binding energy per nucleon varies as a function of the number of protons. So these slices are really just the plots that we made just a minute ago. This surface is the result of stacking these plots together for A values from 1 to 250. Let's take the slice at a mass number of 56. This is the first plot that we made. And up here at the top, that's iron 56, right up near the top of the surface. Now, let's take the slice at the mass number 238. This is the second plot we made, and here's uranium-238. Now, for visual clarity, I only plotted every 10th slice to start out with, so let's fill in the surface with the rest of the curves. There's a lot of data here, but there's a couple cool things we can do with it to drive some more points home. What I'm going to do now is take the point on each slice that produces the highest point on the curve and connect them together with a line. This is going to pass right through iron 56, uranium-238, and a whole bunch of other very stable nuclei. I've actually plotted results for way more isotopes than actually exist to illustrate these parabolas, so let's correct that. This is our new plot when we constrain ourselves to only look at isotopes that have actually been observed. If we take a top-down view of this plot, we get a shape familiar to any nuclear engineer. It's the chart of the nucleides. If you've seen the chart of the nucleides before, you probably noticed that the yellow curve, which tracks the highest binding energy per nucleon for each mass number, follows the line of stability very closely, and this is no coincidence. If we take a look at this plot on its side, we get another very famous plot. You'll find this curve in any introductory text on nuclear physics or engineering. It shows us how binding energy per nucleon changes as a function of the mass number. The peak of the curve runs straight up through iron and nickel, two of the most stable elements out there. If you're on the left side of the peak, increasing the mass number by smashing nuclei together to form heavier nuclei increases your binding energy and your mass defect, and thus releases energy. This process is called nuclear fusion. It's what gives the sun its power, and it's the process by which the nuclear fusion reactors of the future will produce their energy. Stars fuse hydrogen into helium, and then helium into beryllium, and so on and so forth, moving up this curve and releasing energy all the while. This process stops when stars start to fuse atoms together to make iron and nickel. They've reached the top of the mountain. There's simply no energy left to be gained from making heavier atoms. We can see all that from this plot. On the right side of the peak, we see the reverse. Here, breaking apart heavier atoms into lighter components moves us up the curve instead, and we release energy in a process called nuclear fission. This is why the fuel in our nuclear fission reactors is all heavy isotopes like uranium-235. I think it's pretty awesome that with just a couple of concepts we've covered here, we can find hints to explanations for big questions like why do stars die when they make iron, and why does uranium make great reactor fuel? Alright, thanks for watching. I hope you enjoyed the video. I'm not going to keep myself to a schedule with uploads in this series. This video took me long enough to make as is. But in the next chapter, I think I want to cover radioactive decay, Q values, and binary nuclear reactions. Hope to see you there.